Ready?
In other news, I discovered there's a limit to how much I can upload on Canvas. That's probably why they recommend using Panopto for videos. So whenever I try to use Panopto though, like I end up getting a bunch of email requests to view files. It doesn't work right. So I'm just gonna upload these on YouTube. Unless like something very student specific happens. So basically, as long as I don't see people's names and the chat doesn't show up on the recording, I think we'll be good. So today we are looking at the shape of a graph. So in section 4.3, we saw a graph can have a local max or a local minimum at certain critical points. So what did we have to do with the first derivative to find where those critical values could occur? Yep, so when the derivative is 0, or the weird case, but it happens. So most of the time we're dealing with polynomials. They're defined everywhere. They're continuous everywhere. You don't have to worry about the undefined. But we are going to start to look at some rational graphs and some log graphs. Log graphs have a limited domain. So that can mean we typically don't look at the values not in the domain because there's like nothing on the graph there. But I suppose a really weird graph could have like derivatives that behave differently. The other big thing is being a critical point does not mean it must be a max or a min. It does not mean it has to be an inflection point. It just means it's a place where the derivative behaved weirdly. Okay, so here we have a picture of an absolute maximum on a graph. And this is asking us to like use words to describe what the graph is doing. So before our absolute maximum, what would we describe the function behavior as? And so what does that mean the derivative will be there? So when a graph is increasing, what are the slopes of the tangent line there? Positive. So the derivative is just going to be positive. Now, very often the graph itself, like because the values are getting closer and closer to 0, the graph itself is typically decreasing, but the y values are all bigger than the x-axis, higher than the x-axis. So it's a little weird to like think through what one looks like versus the other. Okay. At the point, we have a max. And at that max, the derivative is 0. And then after the point, now we're decreasing. And the derivative will now be negative. So it takes some practice thinking about both of them, especially if you're looking at the graphs of both of them, to kind of correlate between what is the function doing, what are the derivative values that correspond to that function behavior. But that's the big thing we're going to be focusing on today is taking an equation and pulling information about the shape of the graph from the equation by using our calculus knowledge. All right, so this particular point, The derivative at that point, it is flattening out. The derivative there is 0. What is the function doing before that point? Yep. I'm just going to say at the point it's flat. And then after the point, it keeps increasing. So what happens with our derivative then? Yep. And then after the 0? So on our derivative, the graph is going to come down to the x-axis, touch it, and then it goes back up. So we see increasing. The thing that is changing here, it appears that the curvature of the graph is a little bit different, but we'll come up with those terms in a minute. So we know maxes and mins will only occur at critical points. But it turns out that we also have to see particular behavior to be able to classify it as a local max or a local min. Before, when we were looking at the absolute max and absolute min, we didn't really care about the behavior around the critical values. We were literally just punching in the numbers, seeing who had the highest Y, who had the lowest, done. Now we're going to be looking at the graphs as a whole. So the behavior on either side is important. So for our max, we're going to have a positive derivative where it equals 0 and then a negative derivative. So the values go from plus to minus. Min's derivative values will go from minus to plus. And then neither, it could be increasing, flat, increasing, or it could be the reverse, decreasing, flat, decreasing. So we're not just going to find the zeros, we're also going to figure out what it's doing between the zeros, which is going to be very similar to what we were doing with particle motion. When we put down the number line, put down the critical values. Okay, so we have a very boring function. F of x equals x cubed. So good news is it has a very boring derivative. So what's our derivative of x cubed? Yep, 3x squared. And now we want to figure out our critical points. 3x squared is defined everywhere, so I don't have to worry about any divide by 0 undefined stuff. So I'm just trying to figure out when is it 0? Yep. We divide by 3, we get 0 equals x squared, so the only spot is x equals 0. There is our number line. And what the critical values mean is they're divvying up the number line into intervals for us. Any number to the left of 0, whatever the derivative value is, that is the same value, like positive or negative, for that entire region. So that's why we can just pick any single number in there, plug it into the derivative, see if it's positive or negative, and then just assign that to the whole region. So we're going to pick some test values. Now, since 0 gives us 0, like normally 0 is my go-to, yes, pick it, because it's easy to plug in. We can't pick 0 because we already know what the derivative is there. So go on either side. So I'm going to pick -1 and +1. And that is really just to keep it simple. So if I plug -1 into my derivative, I get 3 times -1 squared. -1 squared is positive, times 3 is positive. When I test f prime of positive 1, I'm going to get the same thing. Sorry, it's been a while since I've done this, so I'm actually trying to remember how I used to write them. All right, so all right, so this is increasing, 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 flattens out at 0, and then increasing, increasing, increasing. So when I do one of these number lines, once I'm looking at the shape of a graph, I actually start like drawing arrows. So it indicates like what that test is telling me. So positive values on the first derivative tell me the graph is going up. Now, because it's increasing and then increasing, is our critical point a max, a min, or neither? Yep, because it doesn't increase to decrease or decrease to increase. It's just flattening out in the middle. So not a max or a min. And I mean, if you think about the graph of x cubed, like that's the shape. So it just goes up and up and up, always increasing. All right, now we have this idea of concavity. So when I look at the slopes here, I've got all positive slope, all positive slope. But my slope is going from fractions, like this would be 0, this might be like 1/10. Somewhere over here, we'll have a 1. Up here, it's probably like 5, versus here, this is like 10. Our 1 is probably around there. 1/2, 1/5. So the slope numbers along this curve are increasing. The slope numbers along the second curve are decreasing. Hold on a sec. There we go. All right, now we're going to look at the slopes of these graphs as we move from left to right. So I'm just going to kind of sketch lines and then write what those numbers are. So this is a pretty steeply negative slope, like -2. Get to -1 around there. The -1/2, then the 0. So what happens to our slope for the entirety of that graph? Are the numbers increasing as we go from left to right or decreasing? Yep. They start at the negatives and then they go to the positives. So the graph goes from decreasing to increasing, but the slope numbers start negative and go to positive. So what I'm looking at here is like, if I took the derivative and looked at the values of the derivative, my values go from negative to positive, but the derivative itself of this is going to be a positive slope line. Over here, our upside down parabola. Now I'm looking at a slope of like, maybe 3, 1's around there. It eventually bottoms out. Now we've got like a -1, a -3. So now the slope is decreasing. It's going from positive numbers down to negative numbers. So if we look at the derivative of that graph, it's a straight line, a diagonal line, but it's a diagonal line with a negative slope. All right, so let's look at our formal definition of concavity. All right. So if f prime is increasing over an interval, we say that f is concave up. If f prime is decreasing over the interval, we say f is concave down over I. But earlier, when we were talking about the function and the first derivative, when the function was increasing, the derivative of the function was positive. So when our derivative is increasing, the second derivative will be positive. When the derivative is decreasing, the second derivative will be negative. Better be what the next slide says. Yeah. So the second derivative, we're going to do just like the first derivative test. We take the second derivative, set it equal to 0, find our critical numbers, set it up on the number line. Sometimes your critical numbers show up in both lists. Most of the time, though, they're different. And then we can now associate more shape to the graph based on the concavity. So that's why over here, we've got a concave up like a cup, concave down like a frown. My way of thinking about it is a little bit weirder. Like originally somebody was like, we'll see if it would hold cereal. And in my head, I was like, that makes no sense because the cereal would flow out of every one of those graphs. So instead, in my mind, for some reason, changing it to oatmeal helped. So it's like if I plopped oatmeal there, would it stay or would it fall off? So if it's a concave up, I actually will usually like write a little plus in the shape of the graph there. It's like, yes, my oatmeal will stick. If it is concave down, no, my oatmeal would plop back off. Unless it is very, very badly made, in which case don't eat it. So if you can stick to a concave down surface, don't eat. Now we can actually use these two tests together and actually use that information to get a feel for how a graph will look. And we will have a question that asks you to do that on the writing assignment. The homework like splits all the questions. So it'll either ask about the first derivative test or the second derivative test, but it doesn't ever ask a question where you do both at once, which is annoying because it's more interesting when it's all at once. Now, we do have these interesting points called inflection points. So when the concavity goes from positive to negative or from negative to positive, we get these weird points. So here I've got a positive to a negative concavity. So that's the point where the curvature will change. Now, the slope at that point can be all sorts of things. Sometimes it's 1, sometimes like the graph of x cubed, that zero value, that's actually an inflection point because the concavity changes there, but the slope at that point is actually zero as well. So sometimes our inflection points will show up in our derivative, our first derivative test. And see, now we're back to x cubed again. Find the inflection point. So we need our second derivative. So start with our first derivative again. Power down 3x squared. And then power down again. 3 times 2x is 6x. Set that equal to 0, so our critical value is, surprise, surprise, the 0. So above the number line, I like to write the pluses or the minuses. So I usually put my test numbers below the number line. I don't put the tick marks though, because I found when I did that, I'd confuse my test values for endpoints on intervals, and it'd kind of throw me off for answering some questions. So that's why I just have them floating as numbers, and I circle them just to kind of make it distinct from the critical values themselves. So we're wanting to know here, what's the second derivative at -1? And what's the second derivative at +1? So our second derivative is 6 times x. So 6 times -1 is going to be -6. So everything before 0 has negative concavity. And then for +1, 6 times +1 is positive. So everything after 0 has positive concavity. So negative concavity or positive concavity. Now, what I can actually do is pair both of these pieces of information together. So before my first derivative test, everything was plus. So it was increasing, increasing. And now my second derivative test is telling me it's going from negative concavity to positive concavity. I'll lay that on this side. So what you can do then is make a number line with all the critical values. Here it's kind of boring because there was only ever one. And then you can determine the shape. So an increasing graph with a negative concavity, I'm going to like curve my increasing line so it wouldn't hold anything. So that makes it like that. I put the minus there just to be like, that's negative concavity. And then increasing but positive concavity, now I kind of push it from the top and I get a curve like this. How do you know whether it's positive or negative? If it's like positive or negative. So like the first derivative test basically tells us as we go from left to right, is it going up or is it going down? This one tells us like, of those lines, do I curve the line so I could rest something on it? That'd be concave up. Or do I curve the line so whatever it is would fall out? That'd be concave down. So there's actually 4 shapes you can get. So we saw here, there's our increasing negative concavity, increasing positive concavity, and then our decreasing negative concavity and decreasing positive concavity. So those are like the four basic shapes. Yep. So after doing our second derivative test, doing the number, we show the concavity goes from negative to positive. So x equals 0, which is the full point 0, 0, is an inflection point. So the really weird thing is you can actually get a rough idea of the shape of a graph without knowing the function for the graph. So if I give you the function equation of the derivative, you could find the second derivative, and then you can do the first and second derivative test and actually get a feel for what the shape of the graph is without knowing what the function for the original graph was. So you'll be able to say where maxes occur, where mins occur, where inflection points occur. And there's a kind of corollary to the second derivative test. So on the left, we have a minimum. What's the concavity when we have a minimum? Is this going to hold something or is it going to fall out? Hold something, so it will hold a positive amount of oatmeal. Over here, when I have a max, it will not hold. So it would hold a negative amount of oatmeal, if you will. So we can, like, when we have our first derivative and we have our critical values, we can just take the second derivative, plug the critical values in, and see what the concavity is at those values. Sometimes that is less work than picking test values for the first derivative. Min has positive concavity and max has negative concavity. So there's our second derivative test formally written as a theorem. And it's literally just what I was saying. Take your critical points from the first derivative, put them in the second derivative, see if you get positive or negative. And I usually, like, after I do that, I'll kind of write next to it. I'm like, positive, so it's min. Because my brain wants to be like, positive is maxes and negative is mins. It's the other way around for concavity. So I'd recommend drawing a picture, like, just to remind yourself until you get used to it. All right, they're done at Bowerly Garage. All right, so here we just got a compare and contrast. So we're going to do the first derivative test on f of x equals x squared. So f prime of x is 2x. Now look, it's going to look very, very similar to what we just did. I pick a test value of -1 or +1. 2 times -1's negative, 2 times +1's positive. So that is decreasing to increasing. So it is a minimum. Now our second derivative, if I just take the derivative of my derivative, what's the derivative of 2x? Just 2. Is 2 positive or negative? Yep. So this graph is completely concave up. So that also tells us minimum. So you see the blue arrows I drew? Like it's down and then up. If you kind of think about connecting them, then you can see the min better. Ew. All right, so here's a summary slide, but it is not our last slide. But this just summarizes all the information. So with our first derivative, when it's positive, the original function is increasing. When its first derivative is negative, the original function is decreasing. When the first derivative changes, we have a local extremum, meaning a max or a min. On the second derivative, positive is concave up, negative is concave down. When it changes, we call that an inflection point. So the tests themselves are identical. It's take a derivative, set it equal to 0, do the number line, figure out where the pluses and minuses go. So that's why when you start doing these, it's really helpful. Like when you draw the number line, label next to it whether it was the first derivative or the second derivative. Because it's really easy to confuse the two. And now we have this. Hold on real quick, I'm curious. And then we got another. And then we got everything all together. All right. So I'm probably gonna have to do some of these at home later today, but. All right, so this is our function. We could either do this as a product rule, because it's x to the 2/3 times that quadratic, or we can distribute it through, do our derivative, and then we'll end up like factoring out the ugly x part. If we do the product rule, then we're gonna have to do some funky distribution, so I'd rather just distribute it beforehand. So chain rule, it has to be a function outside and a function inside. So if I had like 2x squared plus 7 to the 2/3, that would be a chain rule setup. But here, like one of the ways to see it, I think about is if I put numbers in there and I was going to crunch, like just doing one operation at a time, what's the last operation I would do? So if I put in like, I don't know, 7 to the 2/3 is some ugly number. And then inside my parentheses, I'd have to do 7 squared times the 3/4 minus 12/5 times the 7 minus 9, like crunch all that together. And then at the end, I'd have this 7 to the 2/3 times whatever the result of the parentheses was. So the last thing I did was a product. The ones where it's a big giant fraction, if you crunch those numbers, you do all the top, all the bottom, and then the divide, so it's a quotient. For these, I do all the crunching inside, and then at the end I say, and then I raise that to the 2/3 power. Basically, anytime it's not a product or a quotient, it's typically a chain rule, because you've got one rule that applies for the outside, and then the inside does something else. But it's telling which one you have very much comes from practice. And it's like, I know you don't want to hear, go do more practice, but like, it really does. The more you practice it, the better it gets. But hopefully that'll help like focus your thought process to sort out which is which. Because that was definitely the problem some of y'all had on the test was, is it a product or is it a chain rule? Which is very normal for Cal 1 students to have. All right, let's go ahead and multiply this mess out. So it'll be 3/4, and then it'll be x to the 2 plus 2/3. So 6/3 plus 2/3 is 8/3. Minus 12/5 x to the 1/2 plus 2/3 will be 5/3. And minus 9 x to the 2/3. Now we'll do our derivative, and it's gonna look ugly, and I don't want to use green anymore. So we keep the 3/4 as a constant being multiplied. We bring down the 8/3. And so now you see those ugly numbers they picked are on purpose. The 3's are going to cancel. The 4 goes into the 8 twice. We're going to have a nice integer after we cleaned it up some. 8/3 minus 1/2 minus 3/3 will be 5/3 now. Minus 12/5 times 5/3 comes down. And again, the 5's cancel. The 3 will go into the 12 nicely. 5/3 minus 3/3 will be 2/3. And then the 9, the last one gets a little weird. So 2/3 minus a whole minus 3/3 is negative 1/3. All right, so we'll go ahead and clean that up. So this will be 2 x to the 5/3 minus 4 x to the 2/3 minus 3 times 2, 6 x to the negative 1/3. All right. So we want to set this equal to 0. And then it's going to get a little weird. So we had originally x to an ugly fraction times a quadratic. So the relation between these terms is the powers going down by 1/2 each time. So there should be some way to turn this back into a quadratic by multiplying everything by x to some power or dividing everything by x to some power. And I think I will actually go with the multiplication route. I suspect since this is in here, it means there's something like this on the web work. Because that's usually the only reason Chris puts a problem this ugly. All right, so when I distribute the x to the 1/3, x to the 5/3 times x to the 1/3, two bases, so the powers are going to add. So 5/3 plus 1/3 will be 6/3. Yep. So this becomes 2x squared. 2/3 plus 1/3 is 3/3, which is just x to the first, or x. And then x to the negative 1/3 times x to the 1/3, we add. Negative 1/3 and positive 1/3 becomes 0. X to the 0 is the number 1, so it's just minus 6 times 1, so just minus 6. Now there is a caveat here. When I multiply by this x to the 1/3, I am getting rid of a potential thing, solution. So I also need to account for the case where x to the 1/3 could be 0. If I divided everything by x to the negative 1/3, I'd end up with the same result. But the same thing, when you divide both sides by a variable, you have the potential of dividing out a solution. Multiplying does the same thing. So whatever you multiply or divide by, when you're setting it equal to 0 and doing the solving part, like have that as an extra, let me make sure. Because if you look at the original function, if I put in 0, well, the 0 to the negative 1/3 actually gives me undefined. But in this newer result down here, 0 looks like an okay value. So we just have to remember, like, the equation I have down here has the same solutions as the derivative, but it is not the derivative anymore. It is a different formula now. So all of these do the same thing to both sides. What that always does is it's keeping the solutions the same. So now we're going to solve this. Well, everything there is divisible by 2, so may as well get rid of that. X squared minus 2x minus 3. So Cal 1, Cal 2, pretty much anytime we ask you to solve a quadratic, it can be factored. In almost all of them, the number in front of the x squared term typically divides into the other two. So you actually, most of the time, end up with a quadratic that's just going to be x and x. Then this one will be 3 and 1. We got to make the 3 negative and the 1 positive in the factors. So that would multiply back. X minus 3 equals 0 gives us a critical value of 3. X plus 1 equals 0 gives us a critical value of negative 1. And then we got that 0 from earlier. So those are all of our values. A 0, a negative 1, and a positive 3. All right. So test values here are a little more annoying because we're going to have to use negative 1/2. We can use 1 and 4 and negative 2. And I just tend to use integers because it makes life not so ugly. Now, when you're testing these, we don't care what the number is. We just care if it's going to be positive or negative. So if I plug in a negative 2, negative 2 to the 5th will be negative. The cube root of a negative is a negative. Negative 2 to the 2/3, negative 2 squared is positive. Positive cube root is positive. Positive times negative 4 will be negative. So now I've got a negative number minus a negative, but then it becomes a positive. So I would just crunch it on the calculator. This is not the kind of step that I would go to the effort to like write out on paper. So 2 times -2 raised to the 5/3 close minus 4 times -2 raised to the 2/3 close minus 6 times -2 raised to the -1/3 power. Sorry, my calculator's being stupid. So I'm having to do a hack. So it's negative. Now, the good news is on most calculators, you can go back to your entry and everywhere you put that -2, change it out for -0.5. I'll kill you, calculator. At this point, I'd just say go to Desmos, plug it in there. Well, we can at least do the 1 easily. 2 minus 4 minus 6 will be negative. The 4 is probably going to be positive. So I'm going to put a pause in this because we're out of time. I will finish it at home, post a video finishing it. Let me go ahead and stop recording.